All right, everyone, we are off. How is everyone doing today? Last day of build stuff. You've been enjoying it? Yeah? Yeah, okay. That's a good level of excitement and energy for Friday afternoon. This is a fun talk. There's no really big actionable takeaways, but there's lots of cool, interesting facts, and hopefully you will find it fun. So, a bit about me. My name is Eli. I'm here to talk to you about data storage. I'm on the internet. I'm on Blue Sky now. It's all good. And I currently work for the University of Oxford as part of a research institute, which is very cool. That's not particularly relevant to what I'm going to talk to you about today. I'm going to talk to you about data storage. And what I mean by that is the idea that we, as human beings, need to know more stuff than fits in our heads. And if we want to put stuff outside of our heads, we need to turn it into objects. We need to write it down or put it in a clay tablet or on a hard drive. So this talk is about how we have done that through history as human beings, how technology has shaped the ways that we do that, and how we have shaped the ways that our technology needs to serve us as a result. So, for example, how many people in the room know 3 phone numbers by heart? 4? 5? Yeah. How many people in the last month needed to call a phone number that they didn't know by heart? A lot, right? We need to know things that we don't store in our heads. So that's the problem here that we as humans have been solving for a long, long time. The other thing I'm going to touch on during this is the durability of the way that we store those things. So obviously the durability of the physical medium matters. If I write something down on a piece of paper and then I leave it in the pocket of my jeans and it goes through the washing machine, that's not very durable, right? But that's not the only aspect to durability that there is. If I write something down and then later I don't understand what it is I've written, I woke up in the middle of the night and I wrote potato king or something because I was having a thought, and then the next day it's I don't know what this means. The way I encoded that data was not durable. And that's a stupid example, but here's a more tangible one. Without taking out your phones, can anybody tell me where this leads? Right? This is a very durable piece of information in some ways because you can copy it infinitely. You can take a photo of this and it has the same data in it, but we need specialized equipment in order to retrieve the information out of this. So that is sort of the durability of the encoding of the data, and it's something that there's a lot of people who are worried about us losing the ability to read digital data, and that's a phenomenon that people are calling the digital dark age. See a question in the back? It is Rick Astley. Thank you, Rendell. Of course it's Rick Astley. So, the agenda for today. We are going to talk about old stuff. Before we had electricity, we're going to talk about some early computing stuff. Yes, electricity. Fun, drum memory and core rope memory and all of that good stuff. Going to talk about the things we use today. And lastly, for a bit of fun, we're going to look at some cool futuristic stuff, like sci-fi stuff. So, old stuff. I mean, Bronze Age old stuff. This is a clay tablet. These were traditionally not fired in a kiln, but instead left to air dry, which means that they aren't like pottery that we have today, which is quite tough. They were quite fragile. They were a bit crumbly. So we don't own a lot of these still today. They didn't last. This one we have because the house it was in burned down, If you don't have a kiln, then make your own at home. I don't know. And this tablet is considered to be the oldest known written customer complaint because it is about a copper merchant called Nazir who apparently sold shitty copper. So not only was this guy had customers complaining about him, but then his house burned down. So physically, this was never meant to last as long as it did, and it's an accident that it did. But not only that, the language that it's written in is Akkadian cuneiform. That writing system was lost for a long time. We could not read it. And linguists in the 18th and 19th century said, we know this is language, I bet we can figure it out. And they did, because they were insane geniuses. So both the physical object and the encoding are quite fragile here. It's only an accident that the object survived, and it's frankly a miracle that we can read the writing on it. The history of cuneiform and Akkadian and Hittite stuff, if you're a linguist, fascinating stuff. Old data storage. On the other end of the physical durability spectrum, we've got pen and paper, ink and parchment, pigments on papyrus, that kind of thing. The encoding here is, again, written language, so we have to be able to understand that writing to get the data back out of the object. This photo is of the first 2 pages of the Beowulf manuscript, which was originally produced sometime like 1,000 years ago. We're not quite sure. We don't know when the poem was originally composed. This is the only copy we have. If you are a nerd about medievalist stuff or like fantasy, Tolkien type fantasy, this is an incredibly important text in that literary tradition, and we only have the 1 copy. And it was stored in a library called the Cotton Library. There was a guy named Cotton who collected old and weird things. And for a while, this Cotton Library was stored in a building called Ashburnham House. Does anyone want to guess what happened to Ashburnham House? Caught fire. Yeah. Well, unlike clay tablets, if paper catches fire, it becomes less durable. And a lot of the library was damaged or entirely lost. The Beowulf manuscript was also damaged during this. And this is all very interesting, right? Because we're talking about like old, cool history stuff. But this is supposed to be a tech talk. This is a tech conference. What does this have to do with technology? Now I get to share one of my favorite facts ever with you. The English word technology comes from the same root word as textiles. And this actually makes sense if you think about it in terms of human history. Because what do humans need? We need shelter so we don't die of exposure. We need enough food. And we need clothes to wear and like fabric to make sails for ships and bedding. So you've got like agriculture, you've got engineering, and you've got textiles. And those are the 3 sites of technological innovation. So for a long time, this is a medieval manuscript, and you've got a woman who is spinning fibre, like a sheep's fleece, into wool to be used to make cloth. And you'll see this all over the place in medieval manuscripts, because if you had like 5 spare minutes as a woman in the 14th century, no, you didn't. You were doing something textile related because there was such a demand for it and it was labor intensive. You can see also here, anybody who owns a cat will be familiar. This is exactly what cats do when you're trying to do anything related with string. That cat is trying to get in the way. And this is where we get the English phrase spinning a yarn to mean telling a tale, because women would sit and spin yarn together and tell stories to pass the time. So we can see lots of ways that the prominence of textiles is reflected in our language to the point where technology is started off with textiles. Now, humans like fabric, but it's hard to produce if you don't have something like a loom. In 2nd century China, people invented the draw loom. And people like fabric, and you can see we like fancy fabric. Here you've got some lovely stripes. And with a loom, you can make even more complicated patterns, but it involves like selecting threads very carefully with each time that you weave with draw looms, with looms in general, you have a thing called the warp, which is threads that run up and down, and the weft, which is threads that go back and forth. And with every time that you weave, you want to separate some of the warp threads out. You want to kind of split them in half and pass the weft through. And then you swap them and it goes back. And by choosing carefully which threads go forward and which ones go back, if you've got listed lots of different colours, you can make fancy patterned fabrics. This is incredibly labour intensive to do by hand. And this is where we get the first ever programmable machine. This is a jacquard loom, as mentioned in the Linebreaker song 7-Bit Encoding last night, for those of you who were at the party. And the way that this works is for every hole that is in those tablets, these are punch cards, a little hook can come through and select a thread and pick it up and put it into the half of the warp that gets separated. And if there's no hole there, the hook can't get through. So you are programmatically determining which threads get selected. You can program pattern information into these things, put it into this machine, and suddenly you don't have to select all those threads by hand. You've got a machine doing it for you. And this is where we get punch cards from. That was the original punch cards. Here's some fabric made with a jacquard loom. The ideas behind how this loom actually functioned were developed by a few different artisans and inventors in France, ending with a guy called Joseph-Marie Jacquard, and that's why we call it a jacquard loom. Patterns from the punch cards from the 1700s are still in use today. So big win for data durability there. We have the extant objects, and we can understand what the data in them means. That's pretty cool. All right, we will come back to punch cards later, don't worry. Film photography is an interesting one when we think about data storage because it's a more direct method of capturing information. If you've got a photographic plate, you've got the actual light hitting it is doing the making a physical change. You don't have a human deciding whether or not to put a punch card whole or to write something down. If you're a film photography nerd, you'll probably recognize this. This is the first ever photographically created image by a guy called Nicéphore Niepce in 1826. And this was actually the plate that he used. When light hit it, it hardened this sort of sticky substance that was on it. And so the information was captured in texture, actually, rather than color. And so what we have is that's the sort of the plate, and that's a sort of colorized imagining of it, and it's the view from his window. One other thing, film photography is in a different class to digital photography, because digital photography obviously is sort of storing its data in flash drives and so on and so forth. So it's in sort of a separate category. It's an odd one out in this talk. But one of the reasons I included it is because of this photo. Come on, there we go. This is a very early daguerreotype, the first publicly available kind of photography. And this one is taken by Louis Daguerre, the guy who originated it in the 1830s. It's possibly the first ever candid photo. So these photos, they took a long time you had to expose the plate for a long time, long exposure times, which meant that this photo of a street, or this daguerreotype of a street, people were walking up and down, but they didn't stay still long enough to be captured on the camera, except for this guy who was having his shoe shined. Just stood in place for the correct 10 minutes to be caught on here, and he probably would never have known that he was maybe the first ever person to be captured on candid photo, which is really cool. Film photography is still around. Lots of people very nerdy about it, doing all sorts of things like collodion photographs, and another really interesting thing to go and look up more about that I could do a whole talk about. Right, the next thing I want to talk about, and this is the last one in the old stuff, no electricity, is vinyl records. So who collects vinyl here? Yeah, we got some vinyl enjoyers in the room. The reason that I'm calling them out here specifically is they are the first example of a paradigm that we'll see again and again as we go through this talk, of you have a spinning disc, and then you have data recorded on a spiral, and a head that sort of sits somewhere and reads off that disc in a spiral or in concentric circles as the disc spins. This is something we see again and again and again. Vinyl discs have a single spiral track coming outward from the center, and the data is encoded as texture. So, as any vinyl nerds will know, they're very sensitive to being touched, handled, scratched. You can see a really close-up. You can actually see that is the sound data encoded in the disc. We get the phrase "like a broken record," meaning something that's repetitive, because if you have a scratch on the disc, it can cause the needle to skip backwards and replay the same section over and over. So physically, these are pretty fragile, and you need specialized equipment in order to get the data back out of them. If you just look at this, you can't tell me what song it is. I don't think it's Rick Astley, but it's just from Wikimedia. So you need specialized equipment to read this. They are pretty fragile. However, because there is a devoted community of people who are keeping the art of vinyl alive, they persist. Right, we are now into the early history of computing. And we're back to punch cards. For the 1890 US Census, a guy called Herman Hollerith developed machines for tabulating census data, and all that data was stored on punch cards. This guy, Herman Hollerith, he later founded a company that got merged with a few other companies and eventually became the corporation that we know and love today as IBM. And the concept here is the same as with the loom. If there's a gap in the card, a connection is able to be made. In the case of the loom, it was a hook connecting with a thread, but in Hollerith's tabulating machines, it was a spring that dipped down into a pool of liquid mercury, allowing an electrical connection to be made. And that's obviously very safe and healthy to be around for long periods of time. Something you might notice here is that this punch card has 80 columns. See, there's 80 all the way from. And this is where we get 80 characters per row as a programming convention, eventually. This is the first time that somebody made that choice, and it just stuck. And obviously, these days, we don't have these limitations, and depending on your particular code formatter, you might not do 80 characters per row, but this is where that comes from. Punch cards for data input were eventually superseded by magnetic storage of various kinds, and we'll see those now. These are drum memory storage units. This is the first time we see magnets being used for data storage. Magnetic storage works like this. You have some sort of magnetic surface, ferromagnetic material, that's iron, cobalt, nickel, or certain rare earth metals, arranged in a sort of certain crystalline structure, and you can manipulate their magnetic polarity of areas. You get ones and zeros. You magnetize it one way or the other. Drum memory here works by having a cylinder, essentially, and then that's all coated in that magnetic material, and then data is arranged in sort of circles running along the drum. And those circles are called tracks. Here's another photo of one. This is from a Polish computer called the ZAM41. And the thing about this, the way that you read data from this is you have heads that go and sort of go to the right place on the disk, on the drum, where memory is stored, where data is stored, and reads it off. Now, if you've only got one head, it might take a long time for it physically to move to the correct part of the drum to access the data that you're looking for. That's called seek time, the time spent seeking. And if you have more heads, each one doesn't have to move as far, so you can have faster access read and write times, but it's more expensive to manufacture. So this ZAM41 has one head for each track of data. And these were often used as the primary memory, like the RAM, essentially, of early computers. So the access time was really important. But this is another theme we see again and again. This was expensive to do, and so not very many were made. And so you have that trade-off between better access times or better data density or something versus the cost of manufacture and of upkeep. Right. But if we're thinking about RAM, an early computing RAM, this was the king for a long, long time. This is core memory, dominant form of random access memory for decades. And this was so ubiquitous, it was just called core. You've got all these rings of magnetic material, and then they represent bits, ones and zeros. And their magnetic state is manipulated by these copper wires that run through them, and you can send current through them. And if anyone's done sort of physics at university or like just up to university, you know that that can change the magnetic polarity of a material when you send current through the middle of it like that. But one of the things about this is that reading from the core will also wipe its state, which is called destructive readout. So I can't know the data that's in there without removing that data from there. One neat fact about this kind of memory, it was heated rather than cooled to make it more efficient. The constraint here is not that it should have a cool temperature, but that it should have a constant temperature to be the most efficient that it can be. And it's a lot easier to heat things up than to cool them down. So using smaller and smaller cores and wires allowed the core memory here to reach like very high density of storage in terms of space. You didn't need as much space to store quite a lot of data. And manufacturing it became very labor intensive. It was a process done by hand. It was like lots of threading things through. And for working memory, this was the working memory for a long time. It was eventually superseded by RAM. I'm not covering RAM in today's talk because it loses its data when it loses its memory. It's volatile memory, and I'm only talking about non-volatile memory. Should have mentioned that. But this is was the working memory of computers. But if your computer crashed, all of its state would still be here, and that's where we get the phrase core dump. Because you could still look at what the working state of your computer was at the time it crashed, because this doesn't lose its data when it loses power. Right, this is one of my personal favorites. I think it's really cool. This is obviously hardware, but it's also software. This is core rope memory, and this is read-only memory. The process of writing to this memory is done during its construction. The topology of the wires, how they're threaded through each other and through those magnetic rings, that encodes ones or zeros. Like you thread it this way, it means 1. You thread it that way, it means 0, at a very simplified level. And if you want to reprogram this, you've got to do lots of complicated threading or unthreading or cut some wires or something. And this type of memory was given the name Little Old Lady memory, or LOL memory, because the process of making it looked like thread crafts, textile work, right? The most famous usage of this was in the Apollo missions. And it's a great choice for trying to put software into space, because it's very stable. There's no bits flipping here, you know? If to change what this memory means, you have to do some complicated threading and unthreading. That does not happen by accident. This is very safe to send up into space, and you know what it's going to do, what you programmed it to do. So that's very cool, and it's not used anywhere at all. Have to go see it in a museum. All right, I feel really old putting this in the old section. Has anyone here never used a floppy disk? That number is only going to grow year on year as I keep doing this talk. I brought my homework into school on these. Seen here in 8-inch, 5.25-inch, and 3.5-inch sizes. These were the latest and greatest in removable media storage from 1970s to the early 2000s, so 30 years, a long damn time. They're called floppy disks because the actual storage media is a floppy magnetized sort of, not film, surface. If you've ever taken apart a floppy disk, you'll see they look like this inside. And if you shake them, they'll go boop, 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 boop. But closer up, it looks like this. And you can see, those aren't straight lines. That is the concentric rings again, like a vinyl record. The way that data is stored on here is in concentric rings. And it is by, this photo is taken by a magnetic field camera, and so it's capturing the magnetization, the magnetism of that magnetic surface. So these light and dark bits, that's ones and zeros. So if you put a magnet near your floppy disk, you will affect what's encoded on it, probably quite destructively. Now, one thing about spinning disks and storing data on spinning disks is it's usually arranged so that you have tracks that go round, and within those you will have also data arranged by sector. So here's an area of the disk, and if your disk is spinning at a constant angular velocity, you want to be storing the same amount of data on this as you would on this, because the head is going to read every 0.1 seconds or something. So it means you end up storing data, those magnetic areas, those red and light and dark stripes, like this. And you can see that up here at the top, we're not being very efficient in terms of space on the disk. We could be packing a lot more data in there if we were able to change this angular velocity of the disk. Some disks do this, some types of storage disks do this. Floppy disks don't. Apple did try, early Macintosh computers did have a system where floppy disks spun more slowly when you were reading and writing data to the outer edge, allowing you to have a much more dense packing of magnetization. But it meant that those disks couldn't be read by other drivers, other computers. Again, if you can't read what you've written down, it made the encoding of that data very fragile. You needed even more specialized equipment in order to be able to read from them. So the data durability of those disks was not very good. And it was more expensive to do, so they got phased out. And floppy disks have constant angular velocity. Before computing environments were networked, these were the way that you transferred data between machines. But in February 2003, Dell announced that their flagship home computer would not have a floppy disk drive in it. By 2007, only 2% of computers sold in stores had built-in drives. Floppy disks are coming to an end. They're not quite dead yet. This is from 2019, and this was the US nuclear weapons had been relying on floppy disks in quite a load-bearing way until 2019. So floppy disk is not quite dead. I went on Amazon a while ago and I had a look at external floppy disk drive readers. I couldn't find one with a USB-C connector, but you could get it with USB-A. And if I wanted to read a floppy disk on this computer, I could do that with an external thing. Wikipedia calls this technology obsolescent, as in it's becoming obsolete, which I think is just an incredible word. We are now into, interlude, encodings. This is all the things I've been talking about. It's sort of easy to see, like, we've got magnetization or we've got texture on a thing. We can take photos of this with a magnetic field camera. There's specialized technology that's needed to read data off a lot of this, but a lot of it would be easier to reverse engineer. But as we move into an era where we have more and more technology just around us and we rely on it more and more, it's more reasonable to assume that somebody is able to read off a hard drive, for example. We become less and less able to reconstruct what that data is in the absence of that technology. So again, with the QR code, if we suddenly no longer had the apps that can read it and the software that can read it, all that data would be lost. And maybe, we all know how to find Rick Astley on YouTube, but for more complex data, there are some things that it's only stored digitally, and that is an enormous risk for the durability of that data and that understanding. And this is what people call the digital dark ages, this sort of fear that we will lose the ability to retrieve the data that we've put into objects, and that we'll lose all of that understanding. Yeah, and that the digital dark age is the phrase that you want to Google, and there's lots of people doing very cool and interesting work in that space, like archival, but also trying to design encodings that are reverse engineerable, so that if somebody in 10,000 years comes across some data, they might be able to understand it. And there's lots and lots of really interesting problems that go into that space. Okay, current stuff we're familiar with. More spinning disks, if you can believe it. Does anyone here have a desktop PC with an optical drive in it, a CD drive? Yeah, I knew you would, Randall. Yeah, okay, a handful. Does anyone have a gaming console with an optical drive? Lots more. This is why they're in the current section, because not many computers have them these days, but they are still, you can still get your PS5 games on disk. I'm grouping a bunch of things under this heading, optical media. Laserdiscs, CD-ROMs, rewritable CDs, Blu-rays, DVDs. They all work pretty much in the same way. Spinning disks, and you put data on it in concentric circles, and the disk spins, and you read off of it. And this is what a CD looks like. It's texture, again, actually, like a vinyl record. But instead of reading off of it with something that actually detects the texture, what happens is there's a laser that is shone at this disk, and it can tell the difference in reflectivity between the dips and the bumps in the disk. So you've got like some plastic that's got texture, you've got usually aluminium here for a read-only disk, and then you've got stuff to make it smooth on the top, so that that texture is protected from you scratching it too hard. Obviously, as anyone who's used CDs will know, doesn't make them immune. You can still damage them very easily. This is the detector from a Acer laptop's optical disk drive. And yeah, there's a laser that shines on the disk, and then the light that is reflected back tells that sensor whether or not it's a dip or a bump, ones and zeros. And CD-ROMs were developed, read-only CDs were developed by Sony in 1984. But it wasn't until 1997 you got ones that you could write to at home as well. This is a rewritable CD, and you might notice it's darker in color. Like that's a sort of darker silver, right? And this is because it's not aluminium on that layer of metal. It is actually a silver indium antimony tellurium alloy. Try saying that after the party last night. And what that does is it allows that laser to melt that metal. It's actually got a low enough temperature that you can melt that metal. And when you melt it, what happens is it goes from being very, very shiny, very reflective, to being sort of goopy and dull. So you change the reflectivity of the CD, and that is what encodes data. In non-rewritable ones, it's texture that changes the reflectivity, and in rewritable ones, you're changing the structure of the metal. And then to return it to its original shiny crystalline state, you have to heat the whole disk up at once. So it's hard to erase only part of a CD. That's why you get the phrase burning a CD, from heating it up. Did I see a question? Oh, cool. Please do raise your hands, ask stuff. Right, reading data out of an optical disk requires its surface to be legible. You need to be able to, that laser needs to be able to see that, to reach that metal layer. So if you've got scratches, if you've got stickers, you've got fingerprints on your CD, much like with vinyl, it'll cause you problems. Optical discs don't have protective housing built into them, unlike floppies, so it's a lot easier to scratch them. Has anyone here ever, you've taken your CD out of its player and you've got your little cloth and you're trying to rub it because it keeps skipping back and forth like a vinyl disc? And it's the same problem. It's that, damage to the surface of it causes problems in reading the thing. So physically, these are, they're less fragile than pen and paper, right? But they're still pretty fragile and you've got to take care. Okay, magnetic tapes. Who is confused as to why these are in the current section? Right, thank you for being an audience participator. These are in the current section because they are used very heavily in cloud storage. So this is one of the first bits of sort of computing stuff that I'm talking about where the access to the memory in here is not random access. So with a spinning disk, you can just move the head and suddenly be in a completely different area of the disk and of the data that you're reading. With this, you got to scroll. If you borrowed a VHS tape and you had to return it, you had to scroll all the way back and it would take ages. It's not random access, it's sequential access. The way that these work is They're ferromagnetic material, bits are magnetized, ones and zeros. We are all familiar with this. These are some of the earliest tape drives. They were used to record computer data in 1951 for the UNIVAC 1. IBM quickly followed suit and set standards, and they've been in pretty constant use ever since. So I used to work for a cloud company, and one thing that cloud companies do is almost all of them do a thing called cold storage. And this is when, let's say you have security footage or like compliance documents, and you don't need to really update these ever. You don't even need to look at them that often, but you do need to have them stored. And a really good way of doing that is to put them onto magnetic tapes, because it doesn't matter that it's slow to access them and that maybe someone needs to go to the physical warehouse and put a tape into a tape reader. If you can accept that maybe there'll be a 24-hour wait to get your data, these are great. They're energy efficient because they're never plugged in. You plug them into a tape drive only when you need them. It's very stable. The magnetism of tape is very stable as long as you don't put magnets near it, like that picture of the floppy disk. And they're very cheap to manufacture. So a lot of cloud companies do their cold storage of data with tape drives and magnetic tapes. One of the other uses of these was in 1976, NASA put a Viking lander on Mars. You can see Carl Sagan here with a replica. We didn't send Carl Sagan to Mars. And it recorded a bunch of data to magnetic tapes, like this piece of machinery. NASA got the tapes back when the lander returned, and then they left them in a cupboard for 10 years. I'm not quite sure why. But when they got around to trying to read the data off of these tapes, the data was all still there, very durable method of encoding, but they didn't know what it meant, because all the people who had worked on that project had either died or left NASA, and they had to go back to the hardware of the lander to figure out what it had been magnetizing when it was writing that data. They had to reverse engineer it from scratch. So that's an example of the digital dark age, you know. All of that time and effort and money and expertise and technology that was used to send this lander to Mars, and we nearly lost all the data off of it because we nearly lost the ability to decode it. Right, more spinning disks. There's so many spinning disks in this talk. Hard drives, we all know them, we all use them. You get them built into most personal computers these days, unless you're SSD only. You can get external ones that will hold a lot of pirated media. I think we're up to about 20 terabytes that you can get commercially. And these are the same as floppy disks, vinyl, things spins round and round, you read data off of it. The medium here is, again, magnetism. So don't put your electromagnets too near to these. Once again, it was IBM who pioneered these. These came out in 1957, and these each, there's two of them here, these two big blocks, these each store 3.7 megabits or megabytes of God's own data. They had 52 disks each, one arm holding two read-write heads. IBM kept iterating and improving on this. And again, they pioneered a model that had more heads, one read-write head per data track. They were too expensive to build and maintain, so they stopped doing it. And over the 1980s, hard drives went from being a really expensive add-on to just standard issue. And we have a close-up picture of one here, again with a magnetic field camera. Modern hard drives have got to the stage where the areas that are being magnetized here, you can see that says 200 nanometers. The areas that are being magnetized to represent bits are so small that they risk losing their magnetic state due to a quantum effect called superparamagnetism, where heat can cause a magnetized material to flip its polarity, turn a 1 into a 0, vice versa, in areas smaller than 50 nanometers. And you see this is 200. A quarter of that, we are looking at areas that small at this point. And for reference, the thickness of a piece of copy paper is somewhere between 70,000 and 180,000 nanometers. So we're talking microscopic here. And the way that we've addressed this problem of just sometimes bits will flip is hard drives are actually now made of 2 layers of magnetic material, polarized oppositely so that they attract each other, and separated in the middle with 3 atoms of ruthenium, which is not magnetic, so that those 2 disks reinforce each other enough to overcome that quantum effect of superparamagnetism. But we made the magnet so small that the universe doesn't like it. It's so cool. It's so cool. And that's a hard drive. And if you've got one in your computer, you've got, you're dealing with quantum there. So great, quantum computing, I guess, technically, sort of. Anti-quantum computing if we're trying to combat a quantum effect. Right, flash drives, flash memory. You've got some of this in your pocket, probably. It's what your phone runs on. Smartphones, tablets, if you've got a YubiKey or other 2FA token, that's got some flash memory in it. And SSDs are flash memory as well. So these work by using a circuit component called a floating gate MOSFET, which is extremely complicated, but basically it's a bucket that you can put charge into. And if it's got charge in it, it's a 1. If it doesn't, it's a 0, at a very vague, simplified level. And it draws power from whatever it's interacting with. It doesn't need an external power source, unlike HDDs. Whether that's over USB or integrated directly into a circuit board, it will just draw power from its sort of host machine. And this makes them great as removable devices, so plug and go. And I moved from writing my homework and putting it on a floppy disk to putting it on one of these when I was in school. They have a few limitations, though. For a given block of storage in a flash drive, you really want to write to it all at once, not in patches, just due to sort of technical hardware limitations. They also have a lifetime limit on how many times you can write data to them, because the gates, those floating gate MOSFETs will wear out over time. The more times you put charge into and out of that bucket, the more fragile it gets, sort of. And these components end up with wear, and flash drives and SSDs have a piece of hardware in them that will try and spread that wear out over the whole device and make sure that when it, you get the maximum usage out of all of them, and then they all fail at once, essentially. And another problem is that these MOSFETs will leak charge over time. Those buckets have got tiny little holes in them, essentially. If you have a USB, put some data into it, and leave it in a drawer for 10 years, you might not be able to even get the data out, let alone if you don't understand how to read what's on it. It might be a bit garbled. And this happened to me with my wedding photos. Thankfully, the photographer had backups, obviously, because she's great. But yeah, flash drives are not that durable. They are not in strong contrast to magnetic tapes. These are not stable ways of storing memory long term. All right. So that's all the current stuff. We've learned all about the history and the current state of data storage. We know a bit more about how and why various types are used for various purposes. And all the things I've just talked about are probably going to get incrementally better over time, right? We're going to be able to have more and more data put onto a hard drive. We're going to have, better, the things I talked about with flash memory, like the lifetime wear. Those are the lifetime wear limit on an SSD that you have in your computer now is orders of magnitude more than you will ever use. It's functionally not a problem anymore. All of these things will continue to get better and better, but that's not cool and sexy. I want to talk about cool and sexy stuff. Let's talk about some futuristic sci-fi things. DNA. We can store data in DNA. DNA is very stable at low temperatures, and it's incredibly data dense as a physical thing, right? Microscopically small cells can hold the entire genetic code for an entire species. And there's a team at Los Alamos who've created an encoding called the Adaptive DNA Storage Codex for turning computer-friendly binary into the pairs of A, C, T, and G bases that make up DNA. And the idea is you make synthetic DNA that represents your data, and then that could be stored durably at low temperatures for decades. We can do this today. It's not very efficient in terms of time. There's DNA data on the moon, actually, courtesy of the Bereshit lander in April 2019. It went to the moon, and it was carrying some data encoded in DNA. It did crash, so we don't know if that data is actually still up there. But if it is, then the people who ran that mission, the Arch Mission Foundation, they estimate that data could be stable physically for billions of years, which is kind of mind-boggling. But of course, the question is, will anybody be able to read and understand it in those billions of years? One last thing on DNA data. I thought this, when I was originally researching this, I had the idea in my head that it was we're going to encode data into the DNA for a bean plant, and then you can replicate it infinitely, and it's not that. That's a bit more Jurassic Park, and we're not doing that. Not because I think we don't have enough mad scientists who would play God, but it's just not happening. Right. This is Superman storage. It's named after the Kryptonian memory crystals in the DC universe. It's also called 5D optical data storage. And what this is a bit of transparent material, so toughened glass, fused quartz. and you use a laser to engrave data within it. So like little spots of whether or not, like of opacity, essentially, within this material. It's called 5D basically as a marketing thing. The idea is you've got, your 3 dimensions of space, right? And then you've got the angle that you're looking at it from and how close you are. And that's 5 degrees of freedom, 5 dimensions. It's a bit cheeky to call it 5D. The photo above here is it's the Universal Declaration of Human Rights, engraved into a piece of glass with the UN logo in it, which is pretty cute. I don't know what encoding is being used here. I don't know how they turned 7-bit ASCII, let's say, into this particular spatial arrangement of dots of opacity. But if we are able to preserve that encoding, that translation, people in indefinitely amounts of time could be able to read the UN Declaration of Human Rights off of this. Because if you don't drop this, it's not going anywhere. You're not going to have charge leaking over time, or So we've kind of solved the physical durability problem with this particular storage medium. And so the real problem here is about the encoding. Yes, Randall. I don't know. I was wondering that in my head. So the question was, how big is it? In my head, it's like a little coin, but I genuinely, I don't know. It's from Southampton. There's the link there. So I'll go look that up. But yeah, it's cool. It's very cool. Both Hitachi and Microsoft have been working on this concept. The current bleeding edge stuff is being done in Southampton. All of these teams are working on it with the explicit goal of durability, being able to preserve information and data for the far future. And if we still know how to turn those bits of opacity back into understanding in 1,000 years, this will do the job. Okay, last bit, we've got 3 minutes left. So, time crystals. Let's get really weird with it. Do we have any condensed matter physicists in the room? I have had people raise their hands during that before, and which scared me immensely. This isn't a time crystal. This is a space crystal. And like flash memory, you probably have one in your pocket, because that is silicon. And the thing that makes it a space crystal is that it has a repeating structure in space. One area looks much like another. If you translate in space and move over, the two things look pretty much the same. They've got the repeating structure. Time crystals are the same, but for time. They have repeating structures in time. And this is the best picture I could find to represent this concept. There aren't photos that I can see of real time crystals. They do exist. A time crystal is an object whose lowest energy state, its resting state, is one of motion. This doesn't break the conservation of energy because something quantum physics. They were first theorized to exist in 2012, and in 2021, only 9 years later, a team of scientists in Hamburg actually made one in a lab. It didn't look like what you'd think of as a crystal. It was goop, essentially. It is a Bose-Einstein condensate, which is a state of matter you can get when you supercool boson gases. I hate it when I've opened my freezer and I've actually accidentally made a Bose-Einstein condensate again. But the reason they're in this talk is because some very clever people think that we might be able to use them as some kind of persistent memory storage for quantum computers. And I don't know anything more about it than that, so please go to Wikipedia if you have questions on that. But the storing memory for quantum computers is kind of currently an open problem because there's a thing called in quantum theory, there's a thing called the cloning theorem, which states that you can't duplicate quantum state, you can only transfer it. Any storage of memory would have to have destructive readout, just like core memory. If you're going to read from memory, you have to also destroy that storage, which is, we're not used to that anymore in computing, right? We're used to being able to just copy state indefinitely, infinitely. But yeah, time crystals. But you didn't think you'd be learning about time crystals today. But there they are. Right, conclusions, because we are just about out of time. Learned about storing data all the way from the Bronze Age, clay tablets, people complaining about shitty copper, all the way to DNA encodings and becoming human information cyborgs. This is a very incomplete and whistle-stop tour. The full version of this talk is about 6 hours long. Most of what I want to impart here is that humans are cool and creative, and we're very good at making increasingly complicated hardware. But the other takeaway is that data is useless if you can't understand it, you can't read it. When we make decisions about how and where we store our data, it has to be with durability in mind. If we store data, we should probably make sure that we write somewhere down like how to read it back out. If they'd done that in 1976 with the Viking lander, it might have been a lot easier to retrieve that data. All of this technology is useless unless another human being, maybe your future self, maybe somebody else, can use it. Yeah, all right. That's me. That QR code is not Rick Astley. That takes you to a little feedback form where you can tell me what you thought of it if you're so inclined. Find me on Blue Sky. Come and talk to me for the rest of today. And please do enjoy the rest of this conference. Thank you for your time and attention.